All right. Greetings, YouTube. Greetings, students. Give me just a moment. We got people coming in. Yeah, that's what we want. We got this person and this person. All right. So let me see. Make sure my audio is working. Give me just a moment. Ali Oxenfree. Okay, so we're gonna go with it. Greeting. I'm gonna have to turn the music down. It's totally distracted for me. So greetings, scholars. I hope all is well. I owe you all a lecture, so that's what we're gonna do right now. Is the one that I owe you. I meant to do it over the weekend. Just you know how time flies, right? Let me look at my calendar really quickly. I know we have finals that first week of May, so that's rapidly approaching. When I look at like my lesson plans, it's really only like 3 full lectures. So this would like this essentially would be like the last week of new material. I think that's how I have it set up. Today we're going to do section 4.4. This is the one that I wanted to do last week. So that was from week 10. Even though this is really week 11, we're going to do the makeup lecture, and then I just owe you all a lecture, right? Okay, so if there aren't any burning questions, let me check one other thing. I'm just going to go ahead and get started with what I intended to do for today. Okay. All right, so let's go like this. Let's grab my pen. All right. So yeah, hopefully you all are having beautiful weather. It's gorgeous here in Atlanta. Like I'm totally exhausted. This is like my second day in maybe 3 or 4 days doing 10 miles on foot. So, so I'm like exhausted. Give me a moment. I need to log the student. It's so weird because like I always want to say you all's name, but I'm trying to like respect you all's privacy. So it's like since we are live streaming on YouTube in the public domain, I try to minimize sensitive information that I put out as much as possible. Sometimes I'm just not able to do it. So it's always weird because I always want to call you all, by name, but that's neither here nor there. Okay. So again, if you're just joining us, this is our makeup lecture that I intended to do over the weekend and I just didn't. We really only have like 3 new lectures remaining. We honestly don't even really have to rush it because I think I factored in an extra week in the way I have everything set up. But yeah, so we have 4.4, 5, and 4.6. I think is the last of the new material that I wanted to do. I think we're basically doing every section in chapter 4 except for the last section. Then we could use the remaining time to kind of review, put things in order, and prepare for the final, okay? So with that being said, again, I do monitor the chat, so feel free to either unmute yourself. Can you guys hear me? Yeah. Feel free to either unmute yourself or type in the chat if you have questions or about anything, okay? All right, so let me see, are you lagging on me? No, you look good, okay. So we're continuing chapter 4 on integration. And so today we want to look at the section 4.4, properties of definite integrals, additive property, average value, and moving averages. The objectives here are to use the properties of definite integrals to find the area between curves, solve applied problems involving definite integrals, and determine the average value of a function and find the moving average of a function. Okay, so we have this theorem 5. So for a strictly less than b strictly less than c, the integral from a to c of a function is going to be the integral from a to b of that function plus the integral from b to c. So say we have some function f, like here, and we have a, which is strictly less than b, which is strictly less than c, right? So you have some b is a intermediate point between a and c. So the integral of the function between a and c, it can be broken up into 2 parts. So we can find the area of this first shape, and then add the area of the second shape. That's essentially what this theorem is saying when you have an intermediate point between A and C. Somehow my run like took my voice. I guess it's the first time that I'm like talking. I was out cold. Like I was so exhausted. I was like, man, getting older is so much fun. That's neither here nor there. So we have this example, and we ask to find the area under the graph of the function from -4 to 5, where this is a piecewise function. When x is strictly less than 3, the function is 9, and when x is greater than or equal to 3, the function is x squared. Okay, let me see. find the area under the graph. So basically, okay, so what it's asking us to do is it's asking us to find the integral of the function. We want it from -4 to 5, but you know, when we look at the graph, it's two basic shapes. You know, this first one is what, a rectangle, and the second one is this, like this region over here, right? So instead of trying to just do from -4 to 5 because it's a piecewise, we can go from -4 to 3, find that area, and then add it to the area from 3 to 5, right? So what I mean by that, we're going to integrate from -4 to 3, and let's just do f of x dx plus the integral from 3 to 5 of that same function, right? F of x dx, right? And essentially what this is going to give us is going to be the integral from -4 to 3. From -4 to 3, the function is 9 dx, and then plus the integral from 3 to 5 of x squared dx. Okay, let me give myself some space. I was just taking that for notes. Let me cut this and move it to the next page. Let's cut. We're gonna paste. Let's do paper. Let's do like this. Let's do view, seamless. And I'm going to say this is enough space for right now. And let me do one other thing. Let me just kind of move this to be a little bit more like what we're used to seeing. Something like this, all right? So we saw the image, right? We're basically finding the area under the rectangular region and then the area under the second region, okay? And so that's where this came from. So now the integral of 9 is just going to be what, 9x? So the antiderivative is going to be 9x. We want to evaluate that as x goes from -4 to 3. Then we're going to say plus. The next integral is going to be what, x cubed over 3 as we move from 3 to 5. Okay. I think this student got attendance credit. Let me just check and make sure. Use with the oh. Yeah, he already got a credit today. I think he got bumped off. Okay. Okay, so hopefully, you know, this is okay. This is what we've been doing for a while now. So then for the first part, 9 times 3 is what, 27 minus -36. That's if we plug in the 3 and the -4. And then we're going to say plus, was that 125 over 3 minus 27 over 3. Okay. If we keep going, double negative is positive. That's going to be 50 plus 13 is 63. So that's going to be 63 plus, let's see, if that were 20, that would be 100. So that's 98 over 3. That's a 17, so that's not divisible by 3. Let's do this. So this is going to, we can use a calculator. I'm just playing around doing it by hand. Let's see, that's a 3. They're what, 2, and the remainder is what, 2? 2/3. So then it looks like this result is what, 95 and 2/3? 95 and 2/3. Hopefully that made sense. Again, if anything is not clear, feel free to either type in the chat or unmute yourself if you have questions, okay? We're gonna go with this result. So now let's look at our, let's compare this to our prepared notes. So we got 95 and 2/3, and you see it there. And I think they essentially did the same thing that we did. Okay. All right, let's look at another example. Oh, that's a quick check. Okay, I usually leave the quick checks for you all to work at your own pace. So we have this theorem 6. So it says let f and g be continuous functions and suppose that f is greater than or equal to g over some closed interval ab. Then the area of the region between the two curves as x moves from a to b is basically, okay, so say we have this function f at the top and we have this function g, right? And here between the closed interval a to b, f is entirely above g or greater than or equal to g on this interval, this closed interval. So if we want the area of this region between the two curves, basically what we're doing is the area under F, which is all of this, minus the area under G, which is this region down here. So we're getting rid of that region there. So if you say the area under F minus the area under G, what's going to be left is what's between the area between those two functions. Hopefully that makes sense, right? So if we want the area between two regions where F is greater than or equal to G on that closed interval, basically you just say the integral of the difference of those two functions. Okay. So find the area of the region that's bounded by the graph where F is this, G is this. Okay. So first we looked at the two graphs. So I just went on and used instead of drawing the graphs, we could have drawn these, but I decided to just use the digital graph for the sake of time. So we have f of x equals 2x, which is that diagonal line, and g of x is x squared plus 1, which is basically a parabola that's been shifted up by 1. So we see that they intersect at 0, 1, and 2, 5. So then we can evaluate the integral as x moves from 0 to 2, right? So let's see. So we're gonna if we want the area bound by the two regions, f is above g between 0 and 2. So we're going to integrate from 0 to 2. Basically, we want to say f of x minus g of x. We're going to say f of x minus g of x dx. And, all right, I'm going to have to do something real quick. This is going to be the integral from 0 to 2. This is going to be 2x plus 1. I'm going to clean this up. Minus x squared plus 1 dx. Okay, I just writing that for out so we can have a copy. I'm going to cut this and move it to a clean page. Okay, and let's do our seamless view again, and I think that's good, and let's paste. All right, so that's what I just wrote. Okay. Whew, man. Trying to hold on to my youth, man. I'm so tired. I keep talking about the 10-mile run. I did it early today, knowing, I mean, it's okay. I knew I was going to have class, but I was like, I got to move. I got to sweat. And it's almost like the heat snuck up on me because I started about 11 and it was cool. I was like, oh, the weather feels nice. Let's just go. Man, fast forward like a couple of hours. It's like, fuck. It's like, it's hot. I was like, oh, I got to get back to the car. I was on a trail. And so I was like, oh my God. So, but I made it and I had the dog with me. So, we made it. Obviously from here presenting. Anyway. But I just bring that up because I'm totally zapped energetically. I'm totally tired. We can let's go ahead. I mean, there's a number of ways we can approach this. The simple thing to me would be to just simplify that difference first and then find an integral. So let's do that and see what happens. 0 to 2. If we distribute the negative, this is going to give us negative x squared. I think the 1's essentially going to cancel plus 2x. dx, right? I just want to simplify it. Okay, so we know how to integrate this. This is going to become negative x cubed over 3 plus x squared, right? Because it would normally be x squared over 2, but then the 2's would cancel. And we want to evaluate this antiderivative from 0 to 2. Okay, so then if we plug in 2, that's going to be negative 8 over 3 plus 4. Then we got to plug in 0. If we plug in 0, it's just going to be 0. So we don't have to worry about that. So then let's get a common denominator. 8 over 3 plus 12 over 3, positive 4 over 3. Okay. So this is what we got when we did it. And let's compare this to the prepared notes. Okay. Thank you, phone. My phone is always reminding me of different things. Okay. So we got 4/3. Let's see, how do we do? Second, find the points of interest by setting these equal to each other. X is 0 and 2. So we got that from the graph. That's okay. This is essentially what we did. And in 4/3, this is exactly what we got. Let me check the chat. I should have got myself some water. I'm feeling parched. Talking like an old-timey, I don't know. I don't really care. It's just funny. All right. Okay, that looks good. Come on, thank you. So let's move on to the next example. A clever college student develops an engine that is believed to meet all standards for emission control. The new engine's rate of emission is given by this, where EFT is the emissions in billions of pollution particles per year at time t in years. The emission rate of a conventional engine is given by this. The graphs of both curves are shown to the right. At what point in time will the emission rates be the same? Okay, so we want to solve, we want to see, okay, what's that point? So basically set CFT equal to EFT. What is the reduction in emission resulting from using the student's engine? Okay. Okay, so let's set these equal to each other. We got, what's on top? CFT. So we want to set 2t squared equal to 9. Let me write it here. So we have 2t squared. We want to set that equal to 9 plus t squared. Okay. Let's cut. Oh my, she's warming up them vocal cords. And she loves barking. I don't know what that's about, but that's what she loves to do. This is part A. Let's do view. Come on. Seamless. Okay. And let's move this around. Okay. Let's see. Let's set it to 0. So if we set this to 0, we're going to get what? T squared minus 9 equals 0. So then we get what? T minus 3 times t plus 3 equals 0. So then t equals plus or minus 3. Now, if we're talking about time, the negative result doesn't make sense in this context. So then we're going to go, they're going to be equal when t is 3. Okay. So then the second part, what is the reduction in emissions resulting? This is just given by, basically it wants the difference, you know, the area of the region bound by these two. So basically we're gonna take the integral. We're basically trying to find the area of the shaded region. Okay. So then what we're gonna do for part B, we want to integrate, it looks like from 0 to 3, C of t is 9 plus t squared. So we're going to say 9 plus t squared minus 2t squared. Oh, well, that was the result we just got, right? Let's just keep going. Minus 2t squared dt. Okay, and let's add a page. Okay. Okay, so let's find this integral. Okay, so this is going to be equal to the integral from 0 to 3. Let's see, if we subtract, that's going to be what, 9 minus t squared dt. The integral of 9 is going to be what, 9t minus t cubed over 3. And we want to evaluate this as t moves from 0 to 3. Okay, so if we were to plug in 0, it would be gone. It's kind of a repeat of the previous one. So we're going to plug in 3. That's going to be 27 minus 27 over 3. Again, if we plug in 0, that's going to be 0. That's going to be a 9. So I think that result is 18. Let's see. What are the units here? Billions of pollution particles per year. Well, we got a 18 billion. Let me see. So let's go like this. Let's see, how do we do? We're going to compare this to the notes that were prepared in advance. Okay. Let's go view. Come on. Okay. All right. So if we compare, so for part A, again, since the negative time has no meaning in this problem, the emission rates will be the same when the time is 3 years. That was part A. And then the reduction in emission is represented by the area between the graphs of E of t and C of t as t moves from 0 to 3. So that's exactly what we did. Right there, 18 billion pollution particles per year. That's exactly what we got. Oof. It's like when I'm doing math, all I see is math, and then as soon as I finish doing whatever example I'm working on, I remember how much pain my body's in. It's like when I'm doing math, I'm not even aware of it. I'm so like in that question, and then once I'm done, I was like, "Oh, that was fun." And then I come back to this reality. I was like, "Oh, all these pains in my body." I was like, "Man, getting old is so much fun." All right, let me see the time. I think we're doing pretty good on time. Okay. I mean, what is time? You know, yeah, I was listening to something today, and it was like there was a Hopi Indian technique or proverb or something like that, or philosophy. They were like they always spoke in the present tense, you know, because you can never go back to the past and you never make it to the future. So the only time that ever exists is now, and you're always here and now. That's it. Like the rest of it, you're not. You know, there's nothing you can do about it. You know, if and like and he kind of this is like Ralph Smart Infinite Waters, and he went on to like speak on like if you want to get a glimpse of your future, take a look at the future is nothing but a continuation of present moments, like what's going on in the present. So if you want a sense of what's going to happen in the future, just pay attention to what's going on right now, and it's kind of like a domino effect, right? And so you know, as long as the more you kind of focus on the present moment, the more you control you have, because you can't do anything. The future never comes because you're always in the present moment, and the past there's nothing you can do about it, but learn from it and move forward. And I just say that because I find myself getting stuck and looping certain events in the past, and it's like you just got to learn from it and let it go. You can't do anything about people, you know. That's just people. Everybody has a right to live their life how they see fit, provided they're not hurting themselves or anybody else. You just got to let people be. You know, as a mathematician, I always wanted to control everything and everything to be perfect, and that's not life. Not as a human. We have that ability to tap into that energy, but that's not practical in my eyes. But anyway, that's neither here nor there. I'm just rambling. Oh, I need some water. Let f be a continuous function. So we have this definition. So it says let f be a continuous function over a closed interval ab. The average value, y average, over the closed interval AB is given by, the y average value is going to be 1 over b minus a, and then the integral from a to b of f of x dx. So the average. So you got the distance. Okay, that's fine. Okay, let's kind of go with it. So again, if we want the average y value, or y average, 1 over b minus a, and then the integral from a to b f of x dx. Okay. So find the average value of this function on the interval 0 to 2. Okay, let me see, I might have enough space here. So y average is going to be 1 over, in this case, well, let's just write it as 2 minus 0, the integral from 0 to 2 of x squared dx. Okay, basically we're just applying that definition that we just looked up. Okay, so then this is going to be 1/2 x squared, the integral of that is going to be x cubed over 3, and we want to evaluate that as it moves from 0 to 2. That's going to be 1/2, basically 8 over 3, because when you plug in 0, it goes to 0. So then 4/3. There's that 4/3 again. Okay, let's go with this and see what happens. Oof. Okay, you see it there. Okay, we still got a little ways to go. Let's keep going. So Rico's speed in miles per hour, T minutes after entering the freeway is given by this. as long as t is less than or equal to 30 minutes. From 5 minutes after entering the freeway to 25 minutes, what was Rico's average speed? How far did he travel over that time? Okay, so this is a repeat of what we just did. Let me write what we need. So we're going to do the integral from 5 to 25. And actually, we need to do the 1 over 25 minus 5. And then, ooh, we got to write all this. Okay. 1 over 200 t cubed plus 3 over 20 t squared minus 3 over 8 t plus 60 dt. Okay, we need all of this. Let's cut. We can paste. View. Seamless. Okay. I think this might be it. There should be enough space. Okay, let's go with this. Okay. So this is an application of the definition that we just introduced. That's going to be 1 over 20 for that first part. Then if we integrate, that's going to be t to the 4. So 4 times 2 is 800, so negative 1 over 800 t to the 4. That's going to be t cubed over 3. So then that's going to be t cubed over 20. The next one is going to be t squared over 2. So 3t squared over 16 plus 60t. And we want to evaluate this as it goes from 5 to 25. Man, I might have to use my calculator. I was kind of hoping a lot of those fractions would cancel, just hoping, but of course it didn't happen. I guess a simple thing would just be put this in the calculator. I'm going to write it out. We got 1/2. Now this first part, we plug in 25, 620, 25. How many is that? Ugh. 625 times 2. I can't do that one. Let's write it like this. Oof. Negative 25 to the power 4 over 800 plus 25 cubed over 20 minus 3 times 25 squared over 16 plus 60 times 25. Okay, that's the first part. Then we got to say minus, repeat that with a 5. Well, let's just do 5 to the power 4 over 800 plus 5 cubed over 20 minus 3 times 5 squared over 16 plus 60 times 5. Okay, that closes off the second part, and this closes off that part. Okay, so that's what we need to put all of that, crunch that whole thing. I'm going to just use my calculator. I feel like you guys don't need to see my calculator for this. This is algebra. You just got to take your time and be as neat as possible. Whew. Okay, I need to go here. I'm just opening up my calculator. Okay. Done. Let's see, we're gonna reload and refresh. That looks good. Okay. So here is my attempt. So first we got this 1/2. Okay. Looks like a double set of parentheses. Let's do negative 25 to the power of 4 divided by 800. Okay, I think that's okay for that one. Plus 25 cubed over 20 minus 3 times 25 squared over 16 plus 60 times 25. This should close off the first part. Then we want to say minus the second part. We got to do a negative 5 to the power 4 over 800 plus 5 cubed over 20 minus 3 times 5 squared over 16 plus 60 times 5 and double close. Hopefully I got my parentheses correct and I typed it in properly. Okay, I didn't get any errors, so that's a good omen. Okay, when I punch this into the calculator, I got 687.5. Okay. Blah, blah, blah. How far, let me see, average speed, how far did he travel over that time interval? Let me see. What is this giving us? Oh, okay. So, miles per hour? Oh, shoot. Oh, man. We might have to go back and adjust something. Rico's speed in miles per hour. Rico's speed in miles per hour. T minutes after entering the freeway is given by this. That's minutes. From 5 minutes to 20. What is Rico's average speed? Something's off. Let me think about it. Rico's speed in miles per hour and minutes is given by this, all right? His average speed. I feel like I didn't. Something's a little off. Okay, I'm gonna rely on the notes. How far did he travel over this time interval? I'm trying to think. I feel like it's the units is what I'm missing somewhere, because it says his speed in miles per hour, but this is in minutes. So I feel like we needed to convert everything to hours. Miles per hour. So this this mile? This isn't miles per minute. This should be miles per hour, but that looks weird. Let's look at it. So here, I'm gonna go with it for now. I'm gonna go to single page. We did this. We did that. 68. Yeah, I don't know. Maybe did I get that part? Let me check. Oh, you know what? I think that's what I'm missing. That first part. Oh, that's what I typed in. Okay, so for some reason I typed in 1/2. It should have been 1/25 minus 5. That's what I missed. And I was like, that number looked weird. Okay, so I think what we did was fine. Let me go back and fix where I'm missing. I missed something, but I found it. Okay, let me insert right here. Let me insert, and that's supposed to be parentheses. That's supposed to be, let me insert again. That's supposed to be 25 minus 5, or I could do 25 minus 5. But I missed that first part. That should have been, I think I intended to type 1/20. Oh, yeah, somehow, right here, I wrote it wrong. Right here, 20, 20, and that's it. Okay, let's go with that. That should fix it. And it did. Okay, cool beans. So all that happens is right here. 68.75, and that should be miles per hour. Okay, that's exactly what we needed. So I was like, why did it look weird? Okay, I was like, is he in a plane? He's going awfully fast. No, we missed something, but we found it. Okay. All right. Single page, 68 and 3/4, all right, 0.75. Let me do this. So I don't know. I'm pretty sure you guys are gamers, or I'm pretty sure I have some gamers. I only play like 2 games. I've only been playing these 2 games for some time now, years, a couple of years. I only play Dragon Ball Z Dokkan Battle and Mobile Legends. Mobile Legends Bang Bang. And so on Mobile Legends, I really like these games because they're always updating and coming out with new content, new characters to learn. So Mobile Legends just came out with a character called Beatrix. So like I totally like adulting is hard. I totally was irresponsible. I literally stayed up all night, like I just been on a rampage, like learning this character. And literally last night I was up all night. Like I was like, God dang, the sun is coming up. I was like, let me turn this thing off. I was yelling at people, man. But I figured her out. Like I found a build that works. It's just fun because it's like chess and it's so dynamic. It doesn't really stay static. It's always changing and updating. They'll make some little changes and they'll make some little adjustments and it completely changes the dynamics of the game. And basically, Mobile Legends is like a 5-on-5 battle royale. So it's just fun. It's just fun. Okay, so if his average is 68 and 3/4 miles per hour, and he was going for what, 20 minutes? So it's just the conversion from that point, right? Let's do the conversion here really quickly. So if we had 68.75, this is miles per hour. We want the distance. So, okay, we got somebody joining. I'll give him credit. I usually don't give attendance credit. Let me see. Did he already give us credit today? I usually don't give attendance credit this late, but I guess I'm in a good mood because I went running. So I let him. I went on to give him credit. Miles per hour. So let me see. So let's convert this to minutes because he went for what, 20 minutes? So we're gonna say times. So let me see, 1 hour is what, 60 minutes? 60 minutes. And then we're gonna say times 20 minutes. All right, that's how we would do the conversion. So with conversions, you just basically line up your units. So we started with miles per hour, then when we did the conversion, since we had hours on bottom, we put hours on top. We were also given minutes, so our minutes cancel, and the only thing that's left are miles, right? So that's how you would do the conversion. Basically, it's going to be 68.75 divided by 3. Hey Siri, what's 68.75 divided by 3?
68.75 divided by 3 is about 22.9166.
So it looks like he went about 23 miles in that time. Let's see. Yeah, 23, right? Yeah. Okay, so we just did the conversion. Let me move this to the next slide. Cut. And paste. Okay. Okay, let me check the comments. So I was just sharing with your brothers. I usually don't give attendance credit for this late attendance, but it's okay. I'm in a good mood. It's okay. The main thing that I need you all to do is just get your assignment submitted on Blackboard. That's the main thing, and just do your best with attendance. I don't want you to stress about it. But if you get all that stuff in Blackboard, you make a strong case for whatever it is you want to do. Let me see the time. Okay, I don't want to stop too early. Let's keep going. So quick checks I usually leave for you all to work at your leisure. So the next concept that we want to discuss, we have another definition. It says let f be a continuous function on a closed interval ab. The moving average function of the function is given by f average is going to be 1 over L times the integral from x to x plus L of f of t dt, right? Where L is a constant representing a fixed interval of time. Okay. So the moving average function. Okay, so we're going to apply this formula. I'm going to have to write this down. Let's do it like this. The moving average function of x is going to be 1 over L, integral from x to x plus L, f of t dt. Okay, let me cut this. Cut. Okay. So in this example, this is on business moving average. The weekly revenue R of X in thousands of dollars of trucks rentals. x weeks since the start of the year is given by this, where x is greater is between 0 and 10 inclusive. Find the moving average over 3-week intervals. The weekly revenue in thousands of dollars of trucks rental X weeks since the start is given by this. Okay, so let's do this. Let me add a page. Let me do my view. Come on, seamless. We're going to apply that definition that was just introduced. So I'm going to paste it here. And we're going to make that one blue because that was the definition of the moving average. Okay. So for our example, the moving average of the function, the L in this case, it said it's 3 weeks, so that's going to be 1 over 3. Let me think about it. Now as x goes from, it says where x goes from 0 to 10. So we're going to put 0 to 13 because it says x plus L. So it should be, let me glance to see if I'm doing this proper. I am not. T 0 to 3. Where's the 10? That's the function. 1 over 3. Weekly revenue of thousands start of the year is given by this. Let's find the moving averages over 3-week intervals. Let me see. That said it was x plus L. To find the moving averages for the first 3 weeks, we set x equal to 0. Okay. Okay. So then once you set, okay, that's fine. The moving average over the second 3 weeks, that is between 1 and 4. Okay, now we set x equal to what? 1. Success for 3 weeks. Weeks 2, oh my goodness. I didn't realize we had to do all that. Okay, so you see how it's working, right? That's a lot. I might use some software for this. That's interesting. I was totally about to do it wrong. Okay, so it's a moving average, right? So the idea, I mean, we could do it, but it's typed out here. It's not that bad. It's not as bad as what I was initially about to do was wrong. I'm going to just get rid of this for right now. I know this is gonna like save us a lot of time, but I think I'm exhausted. But it's not that bad. Let's look at it. So let's start here and let's go view. I'm just gonna use the prepared notes. So again, the moving average is this function, and this is the one we're working where x goes from 0 to 10, and we're finding the moving average over 3-week intervals, right? So for the first one, so our L is 3, right? Because it said 3-week intervals. First, we set x equal to 0. So then it's going to be 1 over 3 as x, the integral from 0 to 3, 0 to 3 of the function, right? So then I would just use some software to crunch this, right? You can use software, and you get the average for the first 3 weeks. Thus, over the first 3 weeks of the year, trucks rental had an average revenue of 16,000 per week, almost 17,000 per week, right? So then, if we want the next set of 3. So now, when x is 1 to 4. So it's still going to be 1 over L. Now x goes from 1 to 4, and then repeat the integral. Now we got 11.91. I think that's supposed to be, that's probably supposed to be 16. Let me see. Hey Siri, what's 1/3 times 37.73?
1/3 times 37.73 is about 12.5766.
Approximately. What are we missing? Why are we getting different results? 37.73. Let me see the first one. Uh, why does this look like this? I feel like that's a typo. 16, 9, 10. I think that's a typo at the bottom. Because if we look at this one, well, we can't confirm that one. I mean, we could, but without doing the work. So, like, if we continue the pattern though, as we go from now, we go from 2 to 5, right? So we still have our 1/3. X goes from 2 to 5. Integrate that same function. This should be the output, right? And then 3 to 6. It's basically just kind of got to keep repeating. You're shifting it. We did 0 to 3, then we did 1 to 4, 2 to 5, 3 to 6, 4 to 7, and let's see how far do we go. 5 to 8, 6 to 9, 7 to 10. Okay, I think that's it, right? So then the graph below displays R along with the graph of the moving averages over these 7 3-week periods of time. The graph of the moving average retains the general shape of the graph of R, but reduces the fluctuations, making the graph trend easier to see. Okay. Okay. All right. So yeah, that one would have just been basically just doing the same integral several times, but we got to the bottom of it. Oh, let me see. We still got a good amount of time, but I think we're okay. So I'm gonna kind of just let that be for now. So for a section summary, the additive property of definite integrals. Um, this is just a recap. So if we have a, which is strictly less than b, which is strictly less than c, so you have some b between a and c, the integral from a to c of a function is going to be basically you can break it up into parts because b is between a and c. So it's going to be the integral from a to b plus the integral from b to c. The area of the region bound by the graphs of two functions where f is greater than or equal to g over an interval, a closed interval ab, the area is going to be basically the integral from a to b of f minus g, right? So we saw that one wasn't too bad. The average value of a continuous function over a closed interval is going to be 1 over b minus a, and then the interval is normal. The moving average function is going to be given by this, and we saw that in action, all right? So we had to kind of take it step by step. So the way we were initially about to do it was wrong. And I was like, something didn't seem right there. So I looked at it, I was like, oh, I see the difference, okay? So I think with that, we're gonna actually end the session here. Let me kind of pause. So, I just did want to kind of open the floor if you guys had any questions about anything. If you don't have questions, if there aren't any burning questions, then we'll end the session here, okay? And from one beautiful mind to another, enjoy the rest of your day. Take care, guys.